This talk is about locally representable algebraic root factorization systems. So my motivation for studying these is to better understand universes in models of homotopy type theory. So for example, we can look at the cubical set model. In that model, the dependent types appear as maps in a certain presheaf category, cubical sets, together with a certain algebraic structure called a Kahn fill-in operation. And then the universe of small types is a modification of the Hofmann-Streicher universe V for extensional type theory, except that it also allows for these Kahn fill-in operations. And in fact, we have a nice classifying property. So this says that if we have a map F, which is the pullback of V along a fixed map H, then the Kahn fill-in operations on F correspond precisely to factorizations of H through the kind of forgetful map from universe U to the Hofmann-Streicher universe V. So this holds for cubical sets, and in fact holds more generally by a theorem of Licata, Orton, Pitts and Spitters, but it doesn't hold for all presheaf categories. So I wanted to get a better understanding of when this holds and when it doesn't. And for this I used a definition by Mike Schulman called locally representable notion of fibre structure, which I define now. So we're given two Grothendieck fibrations from D to B and from E to B, and then we're given a functor between them that preserves Cartesian maps. So a functor chi. And because it preserves Cartesian maps, it restricts to a functor between the wide subcategories of Cartesian maps in D to Cartesian maps in E. So now I say that chi creates Cartesian lifts if this restriction to Cartesian maps is a discrete fibration. And then when this happens, I refer to the pair D chi together as a notion of fibre structure on the fibration Q. So now a notion of fibre structure may or may not have the property of being locally representable. So there are various ways to define this, but motivated by this classifying property for Kahn fibrations in cubical sets, we can define it as certain presheaves being representable. So given X in E, we define the presheaf chi bar X on the slice category B over Q over X as follows. So we take an object of the slice category, so this is the map I to Q of X, and then we take chi bar of X at sigma to be the set of objects in the fibre over chi of the re-indexing along sigma of X. And then we say chi is locally representable if every such presheaf is representable. It turns out that this is equivalent to a simpler condition that just says that the restriction to Cartesian maps has a right adjoint as a functor between two categories. And as it turns out, if this functor has a right adjoint, it is always comonadic. So in fact we have three equivalent conditions here that all say chi is locally representable. This turns out to be a key notion in the theory of Grothendieck fibrations. For example, if chi is a notion of fibre structure that is also an inclusion of a full subcategory, then we will recover a definition by Representable called definable classes. We can also recover many natural instances of Peter Johnston's comprehension schemes as local representability of certain notions of fibre structure. And this includes local smallness of a fibration. So an important source of examples for me is what I call monadic notions of fibre structure. So here we have a fixed fibration Q from E to B, and we say a monad over B is a functor on the total category that commutes with the Grothendieck fibration together with unit and multiplication maps which are pointwise vertical as natural transformations and satisfy the usual monad laws. So given a monad over B, we can define a notion of fibre structure on Q, which is just the forgetful functor from algebras to E. And then we refer to notions of fibre structure of this form as monadic notions of fibre structure. So not all of them are locally representable, but some of them are. For example, if Q is locally small and T preserves Cartesian maps, then chi is locally representable. So an important special case of these is algebraic root factorization systems. So these won't usually be defined as notions of fibre structure, but you can define them this way, and this is, and I'm going to today, and this is equivalent to the usual definition by a theorem of John Bork and Richard Garner. So an algebraic root factorization system is a monadic notion of fibre structure on a codomain fibration of some category, together with a composition operator on algebras that makes the category of algebras into a double category and the forgetful functor into a double functor. So there are many natural examples that do not preserve Cartesian maps, so we're not guaranteed that they are locally representable. And in fact, here are some natural examples that are not locally representable. So in simplicial sets, there are various ways to define Kahn fibrations. You can define them as having the right lifting property against Horn inclusions, but there are several other ways which do come up in homotopical algebra. So, for example, we can take the cubical set definition and just apply it to simplicial sets. Or we can say right lifting property against push-out product of boundary inclusion and interval endpoint inclusion. Or we can say monoidal lifting property against Horn inclusion. So these all turn up in homotopical algebra, so I put the references in Gabriel and Zisman here in the footnote. And they all have the same underlying weak factorization system, but they give different structures, so they give different algebraic weak factorization systems. And none of these three are locally representable. So I don't have time to give a key proof, but I want to point out some key ideas. So if they were locally representable, then the restriction to Cartesian maps would be comonadic, and so it would create colimits. And so therefore we can show that something is not locally representable by contradicting this. So what I do is construct a push out over here of a diagram over here, and then I construct two different Kahn fibration structures that agree on the push out inclusions. So this contradicts the uniqueness part of creating colimits. Another interesting thing that comes up in the proof is that I use the fact that the interval object is a linear order where the endpoints are the top and bottom element. So this is true for simplicial sets, but it's not just some obscure property, it's kind of a defining property of simplicial sets, in the sense that simplicial sets are the classifying topos for linear orders with endpoints. So now, many examples of algebraic weak factorization systems are locally representable, so it's nice to have a sufficient criterion for showing that they are. And so I do this within the general framework of algebraic weak factorization systems that are cofibrantly generated with respect to a growth-unique fibration. So the idea here is we have a fixed vertical map M from A to B, and then we use this to define a notion of fiber structure. So a lifting structure on a vertical map F from X to Y is a section of the canonical map here, so where these Hom objects are defined using the definition of Hom object for a growth-unique fibration. So they're uniquely determined up to isomorphism by the growth-unique fibration, and they exist by this local smallness condition. But the picture is just that for every commutative square that looks like this, we are assigning a diagonal filler, which is like the diagonal map here. So if this is monadic, then it determines an algebraic weak factorization system on each fiber category, and then we refer to the collection of all of these algebraic weak factorization systems as a fibered algebraic weak factorization system, and we say it's cofibrantly generated by this fixed vertical map M. So I also want to define what tiny is, and again I use the general notion of Hom object in a growth-unique fibration. So I say that an object B is tiny if this Hom functor has a right adjoint. So for example, we can apply this to set index families fibration, and then the Hom objects are defined using Hom set functors. So this would say that the Hom set functors have right adjoint, but also we can work over codomain fibration. And in this case, the Hom objects are local exponentials. So in this case, where we restrict to fiber over 1, this says that the exponential has a right adjoint. So now I can state the criterion. It says that if we have a vertical map M from A to B, and the codomain is tiny, then the lifting structures are locally representable. And then so when they're monadic, we get locally representable algebraic weak factorization systems. So I hope you enjoyed this 10-minute talk. So there's a paper coming out soon, and also this is kind of based on some results in an earlier paper listed there. So thank you for your attention.